All right, guys, we're going to take a look at Activity 113, which is our gears assignment. This assignment is broken up into two parts. We have one for gears, and we have a separate assignment for pulley drives and sprockets. So I'm going to kind of work around some issues we're having right now with being able to see things that I've written on the board. So I'm going to try a different method, and hopefully this will work. If it doesn't, we will try something else. So anyway, we're looking at gears. I would very strongly suggest you read through all this again. This is a lot of the same information I went through in the PowerPoint, but again, it's just good to remind yourself how things work. So they talk a little bit about gear ratios. They've got an example here of how you would calculate gear ratio for looking at the number of teeth of two gears. So they're showing examples up here. They're also looking at examples of how you can do it by looking at diameter or angular velocity or torque. So you've got four different ways we can do this. All of them should give us the same output as far as what the gear ratio is. And so here, kind of in the middle of the screen right here is our gear ratio equations. And again, there are basically four of them. All of these things are equal to the gear ratio. And so you can use the number of teeth to calculate gear ratio. You can use diameter. You can use the angular velocity. And again, angular velocity is got a weird symbol, looks kind of like a W, but it's the omega symbol, lowercase Greek letter omega. And that is what that kind of weird W looking symbol is. And then torque is the last one, and that one is also kind of a weird looking T. That is a Greek letter tau. And so when you see that, that's what that is representing. All right, so we're not going to go through and do every problem like we normally would because this is meant to be an exploratory thing. Obviously, since we are not in class and you do not have access to VEX necessarily, we kind of have to go about this a different route. Now, if you do have access to gears of some sort, I don't know where that would be, whether it be VEX or Lego or any other system, that is great. Use those, build yourself a gear train as you're going through this so you can kind of play with this a little bit and see how it works. However, if you do not have access to any of those things, that is okay. You don't have to use them, but you can. Okay. So anyway, as we're going through here, I'm just going to kind of talk you through what you should be doing. I'm going to try to write some things up here, and hopefully that will show up for you. But that's what we're going to be looking for. Again, more examples here. If you need examples on how to solve things, this is showing how you would use diameter and angular speed to solve for a missing piece. In this case, you're trying to solve for the diameter of an output gear. Like, what does that diameter of the output gear need to be for you to have those two different angular speeds? So again, a lot of examples. Read through the assignment. Don't just skip down to the actual problems part. Here's another example, again, of how do you solve. In this case, we're solving for the number of teeth. How many teeth do I need for my output gear to get the torque I want? If I want to have 300 foot-pounds of output torque and I have 90 foot-pounds of input torque, how many teeth should I have? If my input gear is 30, what should my output gear look like? And so in this case, they're working it out, came out to be 100 teeth. I don't know why they put an N at the end, like that's a unit. It's not. It's how many teeth there are. All right. So anyway, what are we going to be actually doing? So these are all examples. It's good information. Read through it. But what you're going to get down to is we're going to be building gear trains. They're kind of talking about what a gear train is. We've talked about that before in the PowerPoint video. What an idler gear is. We've talked about that before as well. And simple gear trains, we've talked about that as well. And what you're going to be doing in theory is building a simple gear train. Again, if you've got gears available, whether it be Lego or VEX or some other building system that you happen to have gears with, get them out, use them. Hopefully you have some options for this. What I would really, really like, and what I would like to see for you guys, especially if you do not have gears. Now, if you have gears, there's probably a little leeway on this, but we're going to be working with 4 gears. And so that's what we're seeing here, A, B, C, and D. And we're going to set them up into a simple gear train, which just means that they're going to mesh together, tooth to tooth, from gear A to B, and then B to C, and C to D. So they're all going to be on separate axles, and they're going to be turning. A will turn B, B will turn C, C will turn D. Okay, that is kind of our setup. Now, again, if you don't have any gears, that's fine. You don't have to have them. You can just make up some numbers for what the gear sizes are. But if you do have them, you can go ahead and set up your own simple gear train like that. What we will be doing though is we're going to come down here and fill out these charts, and this is where I'm going to try a method and see if this works for us, where I'm going to take a snip of that and hopefully it will let me write on here in a way that you will be able to see it. All right, so what we want to do is fill in on this the number of teeth that you're picking. Now you're going to have 4 different gears, and if you have the actual gears, count the number of teeth that you have. If you do not, you can just make up whatever you want. I'm going to use the ones that are in the VEX system. VEX has 4 common sizes of gears, so I'm just going to use those as my gear sizes to kind of write in here. So you have one that's a 12 tooth gear, you have one that's a 36, you have one that's a 60, and one that's an 84. You do not need to follow my example here as far as which one's which or anything like that. This is just me telling you basically these are the sizes that we have with VEX gears for the basic gears. What you do want to do though is not pick them so that you have the same. Okay, I don't want you to have like A, B, C, and D all the same size gear. I don't want you to have A and D the same size. I want you to pick different sizes. So if you're not using these, you can pick whatever numbers you want. If you want to pick something else in there, if you decide, you know what, I don't want that one to be 36. I really want that to be, I don't know, 20. You can do that. Just about 4 different sizes of gears. That's all we want to do. So pick your gear sizes, and then what we want to do then is come down here, and I'm not going to go through all of this, but I'm just going to kind of show you how to do this. You're going to come down here and get the gear ratio. So we're looking at A and B as our 2 gears. And so I'm going to say it's B to A. That means B is the first, so it's B divided by A. So my gear ratio would be 20 to 12. Now, they want you to reduce it. So if you write 20 to 12 here, that is not correct. We want to reduce that down. So we say, okay, well, what is the common value that goes into both of those? And they both divisible by 4. And so I can reduce that down to 5 to 3. Okay, so that's my gear ratio. It's a 5 to 3 ratio. And then below that, they want you to write this as a fraction. So as a fraction, that just means it's 5 over 3. Okay, so that's what they're looking for. So in this top box, you're writing 5 to 3 with that kind of semicolon or that colon in between them to represent that it's a ratio, just like it shows up above here. And then in the bottom one, you're going to write it as a fraction. So it's not really a big deal. That's all we're doing. All right, next one over, you're going to do the same thing with C and B, and you do the same thing with D and C, and fill in each of those boxes. And then down here where it says product of fractions, you're going to go through and take these 3 values you have and multiply them together. And the reason we're going to do that is because that's how we find the overall gear ratio if we are going to do it this method. Now, if you remember back to the PowerPoint video, hopefully you watched that, the video about the gear ratios says that for a simple gear train, which is what we're building, we don't really care about the middle gear. So B and C in this case are not actually going to affect the gear ratio. So what their final gear ratio should be is whatever the gear ratio between A and D is. So for mine, I have 12 and 84. Then my overall gear ratio should be 84 over 12. Or if we reduce that down, 7 to 1. Okay, that should be my answer. Now, when I multiply these together, that's what I should get. So my product of my fraction should come out to be that ratio. That's what we should be seeing. But the idea here is that we are going to find that by finding the ratio between each part. Okay, so that's kind of what we're looking for. All right, so coming back to here, that's what you're going to do. Down here in these questions, you're going to answer each of these questions based off of whatever gear sizes you picked. So they're all going to be different. So I can't give you like the answer because your numbers will be different potentially. But it is asking how many times will gear A rotate compared to gear D? And how does it compare to the gear ratio just calculated in the table? Well, it should be the same ratio. What we do know is that the smaller one will rotate more than the bigger one because it's going to go faster because it has to do more rotations to, for every 1 rotation of the big gear, the small gear will have to do more than 1 rotation. And so when you get your gear ratio, like on mine I said was 7 to 1, that means that my 12 tooth gear, my gear A, would have to rotate 7 times for every 1 time the gear D rotates. So your overall gear ratio should pretty much be the answer to this, but just keep in mind it's going to be the smaller one has to rotate more than the big one. So when you say, I don't know what you're going to pick, so gear A might be the big one, gear D might be the bigger one, but whichever one's the bigger one is the one that rotates less times. So that's going to match your ratio. For 2, it says if 10 foot-pounds of torque is applied to gear A, what is the output at gear D? So this is going to be one of those questions where you are using the equations they gave you, and I'll go ahead and we'll do a snip of this one too. Let's get a new one up here. All right, I think we may have a problem. Let's see. Okay, we'll see if this works. All right, so if 10 pounds of torque is applied to gear A, what is the output of gear D? So what are we doing? We are taking our gear ratio, which we calculated, and we know that gear ratio is equal to torque out over torque in. So that is going to be what you do. So torque out over torque in, and you want to then plug in what you know. So you have calculated a gear ratio. So you have your gear ratio you calculated. I don't know what your number is, but you're going to plug that in, and then you have your input torque is 10 foot-pounds, and we're trying to find that output torque. So we're going to solve that by multiplying both sides by 10 foot-pounds. So you're going to have 10 times your gear ratio equals your output torque. So that's what you want to look for. So 10 times your gear ratio equals your output torque. But it's just going to be that input torque times your gear ratio gives your output torque. So that's what you're going to calculate here. While we have this pulled up, number 3 asks, how can you make gears A and D rotate in the same direction? And so what are we seeing? Well, we've seen that if we have A, B, C, and D, we have these 4 gears. If A is rotating clockwise, what should be true about B? Well, since A and B are meshed together, they should operate where they rotate the opposite direction. And then C should rotate the opposite direction of B, and D is going to rotate the opposite direction of C. So what you're going to find is that A and D are not going to be going the same direction. So if you want them to go the same direction, we need to change something about our setup. So we either need to take out a gear, add in another gear, but we need to get it so that we rotate D the other direction. The only way we can do that is basically have an odd number of gears in this setup. Anytime we have an even number of gears between our input and output, they're never going to turn the same direction. It has to be an odd number. So we either need to have 1 idler gear, we need to have 3 idler gears. We cannot have 2. 2 will not work. And then the last question is, what will the gear ratio be if A is connected directly to D? And we've already talked about that. That is basically going to be the same as the gear ratio you calculated earlier. So it should be the same number. Now you can actually directly figure that out. Just do D divided by A, number of teeth of D divided by number of teeth of A to calculate that number. But that's what we're going to look for. All right. This is how this ratio between A and D compared to the entire system. Again, that one should be the same. We said that earlier. And then ask about how do gears B and C impact the system? Well, gears B and C are not going to affect the system in any way that involves the angular speed or the torque. So it's not going to affect your speed. It's not going to affect the torque. What gear D is going to do differently because of what B and C are providing as far as impact is going to potentially rotate a different direction. So we can change direction of rotation. That's what B and C will do, is they'll change direction of rotation. The only other possible impact we really have is just changing the length of the gear train. Maybe you want A and D to be a little further apart, or we need them a little closer together. We can adjust the overall size of our gear train by adding or taking away those idler gears. So B and C, from I guess the main perspective is it's going to change the direction of rotation, but the other possibility is it also changes the length of the gear train. So if you need it to be a little further between A and D, you can add another idler gear in there, but then you're going to also potentially change the direction of rotation of gear D. So that's kind of what we have to think about. All right, when we get down to the second part, we're looking at compound gear trains. For compound gear trains, we are really taking two simple gear trains is all we're doing. And so that's what they're trying to show us here. I have A and B, that is one simple gear train. I have C and D as a separate simple gear train. And I am going to connect them together. And the way we connect them together in a compound gear train is by tying the output of one to the input of the other by putting them on the same axle shaft. So in this case, A is my driver gear, B is my output for that one. And I'm going to put that output on the input of the CD simple gear train by putting B and C on the same axle. That way, we're basically translating that torque and rotational speed difference that we got for AB onto C and D. We're giving C the same torque and speed that we got with B, roughly, because they're on the same axle. All right, so that's what you're looking for there. And so for the overall gear ratio for those, you're just going to multiply the two together. Multiply the gear ratio for AB times the gear ratio for DC and get the overall gear ratio for your compound gear train. And we could have more parts into that gear train if we need to, but that's kind of what we're looking for. Okay. And so we'll build our compound gear train. It's going to look something like that. And again, if you do not have actual gears to play with, that's okay. Just pick numbers for A, B, C, and D. You can use the same ones that you use for the other part if you want, or you could pick new numbers. That's fine too. Or if you do have the gears, you can actually build a new gear system. There you may have to be a little bit more selective about your sizes just to get it to actually physically fit in the space that you have. Sometimes if you don't pick well, you have issues with clearance. But you're going to fill in just like we did before. I'm not even going to write this down, but you're just going to fill in like we did before. So you're going to have number of teeth for A, B, C, and D. You're going to find your two gear ratios, the first simple gear train for A and B, second simple gear train for D and C. Find those gear ratios, write them down as fractions. You're going to multiply them together to get your overall gear ratio. Okay. And then when we get down to your questions, how many times will gear A rotate compared to gear D? This is going to be the same thing we saw before. You're looking at that final gear ratio. That final gear ratio is going to tell us what that is. And the smaller gear is going to have to rotate more times, but the ratio is going to be whatever we get here. So it'll probably be a bigger ratio, but the same idea is going to be there. So the smaller gear is going to rotate more times, bigger gear is going to rotate less times. I don't know how yours is set up, so I don't know which one's the bigger one, which is the smaller one, but that's what you want to look at. It's your overall gear ratio, and it has to be as a fraction with whole number values. We can't put like 3.2 to 1. I guess you can if you want, but it would probably make more sense to write it out with the whole number values. Okay. And then number 2, just like before, they're telling you input torque, and so that's your gear ratio time or is equal to torque out over torque in. Just like the problem we did before. Again, I'm trying to leave a lot of this for you guys to kind of work through. We can come back and look at them again later, but all these numbers will be different for every person who does this problem. So normally we do this where everybody's going to have the same answer. This particular case will not be that. So, but just understand the formula here is going to be that your gear ratio, which we calculated, is going to equal torque out over torque in. If they tell you what the input torque is, which they are, you're going to multiply the input torque times your gear ratio to get your output torque. All right, last couple of questions here. Why might compound gear trains be better than 2 gears alone? And we talk about this as well. If I want a high gear ratio, if I want a gear ratio that's 10, 20, 40, something, bigger gear ratios, if I only have 2 gears in a simple gear train, my bigger gear has to be whatever my gear ratio times bigger than my smaller gear. So if I have a 10-tooth gear and I want a 20 to 1 ratio, then my output gear is going to have to be 20 times bigger than my other gear. So if I have a gear that's got 10 teeth, my other gear is going to have to be 200 teeth. And while that is possible, you can have a 200-tooth gear, it's just a little bit impractical. You're going to start getting really, really large gears. Really large gears are hard to build. They're heavy. They're a little awkward to fit into mechanisms. If I have a really large gear, that means whatever I'm putting it into has to be big enough to hold that gear. And so we run into all these problems with having high gear ratios with a simple gear train. And that's just not real practical. So instead, we use compound gear trains so that we can create large gear ratios with relatively small gears. We kind of go back and look at what we were just doing. You know, because I am just taking two simple gear trains and multiplying them together to get my overall gear ratio, I can take two smaller gears, relatively speaking, in each of those gear ratios, those gear trains. And when I multiply those ratios together, I can still get a fairly large output. And then I can actually combine more than two simple gear trains. We're looking at an example of just two that we're multiplying together, but I could have a third one or a fourth one. And so you can build up very high gear ratios with relatively small gears by just continuing to compound that gear train. And so that's kind of what you want to look for. Applications of compound gear trains, they're all over the place. We talked about the little Fisher Price cars that you have little kids drive around. Those are driven with really, really small motors that have very, very low torque, very high output RPM. And what they do is they use a compound gear train to get from that high RPM, low torque motor, and they continually, add to the torque and reduce the speed by using gear training, the gear train, and they use that gear ratio to get it down to where it's actually a decent amount of torque and a fairly low speed, so that when the car is driving, it's not going to move very fast, but it's going to have enough torque to drive around and be able to carry that little get around as they drive their little Fisher Price car. But that is not something that you could do with that motor if you tried to directly drive with that motor. That motor has nowhere near enough torque, and it turns way, way too fast to be able to drive one of those cars that way. So that's an example. Now, there's lots and lots of examples. You can look at clocks and watches if you have old mechanical clock or an old mechanical watch. Obviously, the newer stuff that's electronic won't be that way, but there's lots and lots of different examples, even within modern technology, that still uses compound gears. Because it is by far the best way to go to mechanically change the gear ratio and get high ratios. Okay, so that's the end of that. Again, we didn't really talk about all the things in there as far as like writing them down, but I just wanted to kind of do a quick overview with you so you kind of know what to do. So we'll end it there, and you can pick that up next time with the second half.